Okay, so we're continuing our unit on temperature and the zeroth law of thermodynamics, and we're going to look here at another technique for measuring temperature known as infrared thermography. Now, this technique involves capturing the thermal radiation that's coming off an object, and then using the intensity of that radiation to figure out what the temperature of the object is. It turns out there's a precise relationship between the intensity of light and the temperature of the object. And that relationship is graphed here at three different temperatures. These are known as Planck curves, and we'll show you the equation for these curves shortly. But let's just imagine that you had a camera that recorded spectral intensity, and more on that, what that is shortly, of 2 times 10 to the 7 units. And let's imagine this camera was sensitive to infrared light with a wavelength of about 6 microns. Well, you can see that that corresponds to a Planck curve at a temperature of 320 Kelvin. So this camera would output a temperature for this object, or that point on the object, of 320 Kelvin. So here then is the famous Planck function, and what we're going to do here is spend some time getting used to this function. We'll derive this later in the course. It'll come up several times, and this is just really our first look at it. Now, what is B? Well, it tells us the amount of thermal radiation you get at, so it's the watts of energy that's coming off that hot object per second. Now, there's more than just per second. It's also per unit area, per unit solid angle, per unit hertz, and more on that in a second. But that's where the units come from. So it's watts per square meter steradian hertz. It's a rather unwieldy unit, if ever there was one. Now, there's a number of constants in this expression for the Planck function. Epsilon's the emissivity, more on that later. H is Planck's constant, that comes from quantum mechanics. F is the actual frequency of the infrared light. C is the speed of light. And then down in here, we've got E, the exponential function. And then K is Boltzmann's constant. And more on that later when we look at the ideal gas law. So this is the function that tells us how much energy you get per all of these things. Now, we understand energy or power, we understand area, we understand frequency, but what's this unit here, this steradian? Well, it turns out that it's really the three-dimensional equivalent of an angle. For flat angles, for wedges, we defined the angle in radians as a ratio of the arc length to the radius. Now, where that came from is the following idea. The angle as a portion of the entire circle was equal to the arc length over the circumference of the entire circle. So theta as a ratio to pi was equal to the arc length s, this arc right here, over the entire circle circumference, which is 2 pi r. So that's how we define radian measure. That's the definition of theta in radians. Clearly you could cancel out the 2 pi's and you get this relationship right here. Now that's for a flat angle. What about a three-dimensional angle? Because if this is our hot object here, we're emitting thermal energy in all directions, and our camera is only going to capture a portion of that. Well, this is therefore a three-dimensional solid angle. And the amount of solid angle is going to depend on the area here on what's known as the unit sphere. That's the radius 1 sphere. Now, in Cal 3, you would have defined, or you would have seen, the little element of surface area on the sphere. This is sometimes called the Jacobian, and it's equal to this much here. But of course, we are on the unit sphere, which has a radius of 1. So on the unit sphere, the little element of surface area is just sine theta d phi. And so any solid angle then is just going to be adding up over theta and over phi limits this little bit of area. Now, if we add up the entire circle, then that's the maximum solid angle you can have. That corresponds to theta running from 0 to pi and phi running all the way around. We do the d phi integral and we just get 2 pi. Then we integrate sine theta and we get minus cos theta from 0 to pi, which of course is 2 pi, and then we can just flip these limits and get rid of the negative sign. And then this is cos of 0, which is 1, minus cos of pi, which is negative 1. That just ends up being 2. So there's 4 pi steradians of solid angle over the entire unit sphere. So that's the surface area of the unit sphere. So that's at a distance of 1. If you have, say, a larger distance, then the solid angle as a ratio of the entire solid angle in the unit sphere is just going to be the area A. So if this circle happened to have a radius greater than 1, then this is the patch A, defined as a ratio, or rather divided by the total surface area, the entire surface area of the sphere. So remember, we said theta over 2 pi was a ratio of arc length to circumference. Here we're saying omega, that's my symbol for solid angle, over 4 pi, because there's 4 pi steradians in a sphere, equals the area A over 4 pi r squared. That's the surface area of a sphere of radius r. So what we're talking about here is a point on a hot object, say this tree, emitting radiant energy in all directions, but then some of that radiant energy will be captured by the camera. Now, if we're a distance r away, and if the camera aperture has area A, then the amount of solid angle here that's captured by the camera, omega, will be equal to, just canceling out the 4 pi's, area over distance squared. So that's how we will find the solid angle. Now, this is in units of steradians. Not a radian, because that's a measure of a flat angle or a wedge. This is a measure of a cone angle. And instead of there being 2 pi in the flat circle, there's actually 4 pi in an entire circle. So that's an introduction to solid angle, the units for it, and how we're going to go about finding it. Another parameter that was new there was the emissivity, and that's really just a percentage. It tells us how good a radiator / absorber is this object. For an emissivity of 1, that's a 100% perfect absorber and emitter, so it absorbs everything and emits perfectly according to the Planck curve. So a perfect 100% absorber is also known as a perfect black body, because black objects tend to be really good absorbers. An emissivity of 0% absorbs nothing, and this is like a white body, a perfect white body, very reflective of incident energy. And a perfect white body, because it doesn't absorb anything, won't heat up if you put it out in the sun, because it doesn't absorb any radiant energy. Now, another important thing about our camera is that the photocells don't absorb only one frequency. They're actually sensitive to a small range of frequencies, sort of centered on a certain frequency. There's sort of, there's F plus or minus a little bit on both sides. And this whole range there, we'll just say, is an amount delta F. Okay, so let's imagine we take a thermogram of a candle flame, and we're interested in knowing, how hot is that candle flame. So there's a little bit of, we'll call it a pixel of hot object, and that's emitting energy in all directions. And some of that, there'll be like a solid angle here, omega, will actually enter the camera. So this is intended to be the camera over here, right? The camera looks like this. This is the infrared camera. Some of it will enter the camera aperture, be focused by the lens on a photosensitive surface, and there'll be a little pixel of that photosensitive surface that will have a photodiode on it. And that's going to record the amount of energy that's coming from this point on the hot object. Now, not only are we getting a certain solid angle there, let's clean that up a little bit, but we're also getting a certain range of frequencies. So this is just meant to try and show that this is actually a cone of radiation that's entering this camera. So it's a solid angle, not a flat angle. But this white light, of course, isn't just, isn't white. There's actually red, blue, green in that. And then there's more than that. There's also infrared part of the spectrum and the violet part of the spectrum too. Whoops, that's me. That's not what I wanted to show you. What I wanted to show you was, oh, where did that go? Okay, well, never mind. I just wanted to show you what the spectrum looked like for the sun, and that you'd see that there's infrared light, there's visible light, and there's UV, as well as little bits of other parts of the spectrum. So anyhow, there's a range of frequencies there. So what this camera actually gets, the signal into the camera, is actually the intensity, and that is adding up this Planck function over a whole bunch of frequencies. So this integral is adding up over that frequency range, and also over solid angle. So this is our Planck function, but we've got not just a single frequency, we've got a bunch of them, so we have to add up each little bit of energy from each frequency to get the total energy recorded by the camera. And this Planck function is per unit steradian, so each little d omega of solid angle is going to contribute some, and we need to add up over this entire cone to get the total signal, the total energy that's being absorbed by the camera. So this, of course, is the relationship we derived earlier. Now, we're going to make a simplifying assumption, which is just that it's a pretty small frequency range, and it's not a very large solid angle cone, and consequently that the Planck function b is going to be approximately constant over that. So we're just going to end up, oh sorry, I changed that to f, df. That's new, it's just sometimes used for frequency. So we're just going to, by pulling out that b function, saying that it's constant, we just end up integrating df and integrating d omega, and so that just tells us this is just the frequency range delta f, and this is just the amount of solid angle we have, omega. So this tells us that if we want to go from the energy per unit time per unit area, which is the intensity, and then calculate what the spectral intensity b is, we just have to take that measured intensity and then divide by the amount of solid angle, and then divide by the width of the frequency channel. And then once we've got that spectral intensity, well, we know from the Planck function that it depends on temperature. And we can solve for the temperature once you've got the b function. Let's see if I can do this from memory. 2h f cubed over c squared, and then it's 1 over e to the hf over kt subtract 1. So was that right? I think it's probably right. Let's see, where did that baby go? See how I did. There it is. And yes, f cubed over c squared. That's the only hard thing to remember. Now I could check the units on that, but anyhow, I got it right is the main thing. But the point is that once you have the b function and all of these things are constants, you can solve for temperature. It's not going to be a pleasant calculation, but it can be done. All right, so here's a typical problem, or a sample problem rather. So here's a hot object, the candle flame, and then let's imagine, okay, this is the lens in our camera, and then this is the photosensitive surface on the back of the camera. And we're just going to do a little calculation here to figure out what the temperature of this hot part of the object is, given some data here about what's being received. Okay, so this camera lens has area A, and you'll see because of the lens, each little pixel on the object has a corresponding pixel on the camera surface, camera detector surface. So this will be a photodiode, and that photodiode is going to have a corresponding area on the hot object. So we're going to be interested in what the area of this is, because intensity is the ratio of power to area, and it's got a corresponding area here on the photosensitive surface inside the camera. All right, so here is all the data we need, and we're going to proceed to do this through a series of steps. So what's the power received by the camera? Well, power is just the energy per unit time. So we had 0.25 femtojoules recorded or captured by this single photodiode. A femto is 10 to the minus 15 joules. So that's quite a few photons captured by that in 1.2 seconds. Now, from the power, we can find the intensity, because intensity is a ratio of power to area. So the energy that was received by our photodiode was coming from a unique spot on the hot object. So that's the energy per time coming from this little object, and we're going to divide by the amount of area that that little object had, which is given here as 0.5 square centimeters. So we'll take the power and divide by 0.5 square centimeters, which is 0.5 times 10 to the power negative 4 square meters. So that'll give you the intensity of the radiant energy coming from that point on the candle flame. In order to find the spectral intensity B, we need to know how much solid angle we're talking about here. Okay, well, this point here on the hot object, there's going to be a solid angle. There'll be a cone of light that actually hits the lens, and that solid angle cone has solid angle omega. And the solid angle we've shown is the area of the camera lens divided by the distance from the object to the lens squared. So the lens is a circle of radius 1 centimeter, diameter 2 centimeters, and we're told that the object is 2 meters away. So we square it. So now, with the intensity and the solid angle, we can find the spectral radiance, and that's just the fancy name for the Planck function B. Because the Planck function, we saw if we make the assumption that it's constant, we could pull it out of the integral and then divide through, and we find that the Planck function is the ratio of the intensity to the width of the frequency channel times the solid angle that's being captured by the camera. So, with these calculations above, we have an intensity, or I find an intensity of 4.16 times 10 to the minus 12 watts per every square meter of area. The width of the frequency channel, well, our camera detects over a region of 2 terahertz, and a tera is 2 times 10 to the power 12 hertz. And the solid angle calculation here works out to 7.85, gonna run out of room, times 10 to the power negative 5 steeradians SR of solid angle. So our spectral radiance, our B function, ends up being 2.65 times 10 to the power -20 joules per second per square meter of object area per hertz of frequency range per steradian of solid angle captured by the camera. So once you've got that, you want to solve for temperature, and this is a little algebra challenge for you. You want to write an equation here for temperature, and we'll check it in class. And it's going to involve, well, there should be a term like HF over K out in front, and then there'll be something a little bit ugly inside here. So work out what that is, and then find the temperature that corresponds to this spectral intensity. I got 404.6 Kelvin. So what is that? That's about 130 degrees centigrade, which probably isn't really that hot for a candle flame. But there you have it. This is how we can use infrared light to infer the temperature of an object, and it's a little bit of a discussion for how those cameras actually work. Now, when we meet in class, we will actually look at an infrared camera, and we'll take some thermograms, and then we will talk about another device that also uses infrared, but instead of just having a small part of the spectrum being sampled, it samples the entire part of the spectrum. That's known as a thermopile, and we'll demonstrate that in class.